All right, so we are currently at week 6, and we are going to start chapter 8, which is about data, collecting data from a population, which we call samples, and parameters about these samples, trying to estimation about of population parameters is basically the area of statistics. Chapter 8 is fairly simple chapter. It has lots of definitions, different statistics that we can compute about a sample. So, we are going to talk about some descriptive statistics, some numerical descriptive statistics that we can compute, and we are also going to talk about graphical statistics that helps us to visualize the relationships between different parameters and different populations. And then we are going to start chapter 7, which will be about testing certain hypotheses about or inferring something about population, whether this population is different from the other. This is especially important. The week 7, starting at chapter 9, we are going to spend 2 weeks on, actually 3 weeks, as you can see, 3 weeks on chapter 9, which is very important. You'll be able to ask questions like, we make tests when you do research. You say, I have an algorithm. It runs faster than this other algorithm. And that's a claim. So we usually conduct experiments to compute running times to compare these two algorithms on some benchmark data set, right? So this is the most common thing that is done. We try to be as controlled as possible. We write both of the algorithms in the same language. We run them on the same computer with the same setup, and then we measure the running time. And then at the end, what we do is, if you don't know statistics, we just take the average of those running times and say, okay, my running time is 3.5 milliseconds on the average. The other algorithm's running time is 3.9 seconds on the average. So my algorithm is faster than the other, right? So just comparing the averages is not sufficient, actually. How? Because when we perform an experiment, we are conducting a test on some sample. When you claim that your algorithm is faster than the other algorithm, you're making a claim about the whole population of possible inputs that these two algorithms can be run on. Okay, so what if I run the same algorithms on a different benchmark data set? And this time my algorithm is going to be worse than the other, maybe. So first of all, when there are things like when you're having that benchmark, you should be as, in other words, when you're collecting the sample, you want to be as unbiased as possible to have a good representative of the population. But in any case, there are sampling errors. We cannot, since it's a sample, it's just a sample from the population, our experiment benchmark data set, we're bound to have some differences. And we are going to see, just looking at the average and comparing, mine is 3.5 seconds, the other is 3.9 seconds, my algorithm is faster, I will be always faster than this. We have to actually conduct the hypothesis test, which also takes into account the standard deviation of our samples. For example, what if mine is 3.5 seconds on the average, but standard deviation is 4 seconds, and while the other algorithm is 3.9 seconds on the average, but its standard deviation is 0.1 seconds. In that case, can we really still indicate these two algorithms really are going to run? I mean, mine is going to run faster in the population of all possible inputs. So statistical inferences about these things we are going to see. We'll be able to answer these questions. By the way, after we conduct such tests, when we conduct hypothesis testing in chapter 9, we'll be able to indicate that I'm this much confident. For example, I'm 0.95 with probability of 0.95. I can say that my algorithm is within this distance to, or the difference between my algorithm's running time and this is within this range. Or so we'll be able to conduct tests in that flavor. So this is going to be in chapter 9. As I said, it's really useful. Also, when you compare different things, when you conduct tests like this, we usually collect data, and it may claim something about the algorithms or other things. We should conduct hypothesis testing, which is going to be covered in chapter 9. So knowing statistics will help you if later when you're doing your research, probably you'll remember these things when you're going to present your results at the end of an experimental section. You're not just going to say, this is my algorithm's average is smaller than the other, therefore I'm faster. You'll actually indicate that with this p-value or with this alpha is equal to 0.05 or 0.95 at 0.95 confidence level, I can say that my algorithm is different, smaller. My algorithm's running time is smaller than the other. So you will always have to associate some probability, some confidence to your statements. You will not be 100% sure about our algorithm's efficiency because we have conducted a test on a sample. Okay, so this is a little bit look ahead of what we're going to be seeing later in starting with chapter 8. 9, 10, and 11 is all about the statistics. We're going to see some statistical inference. For example, after we collect data, we'll do tests whether this data is coming from uniform distribution or whether this data is coming from normal distribution. So we are going to be able to test some data sample against a family of distributions in chapter 10. In chapter 11, we are going to try to we'll do some estimation, some prediction, future forecasting about our data by using a very simple linear regression with least square estimation, the simplest form of linear regression. We'll see it in this introductory course. Okay, so, and then we'll go back to simulation of random variables, Monte Carlo methods to simulate different population parameters in the last weeks. And then we'll talk about temporal processes, stochastic processes, probabilities that change over time, or basically we'll see Markov chains. So this is how we're going to end this course. And next week, we're going to have our midterm exam on Friday at 4 p.m. It's going to be an open book, Octave Online. You'll be able to use Octave Online to refer to those cumulative distribution function, CDFs of your family distributions. And it's going to be 2 hours long. There will be about 10 to 15 questions, which are very similar in flavor to the quizzes that we have. Okay, so they are going to be like the quizzes. They're going to be mostly numerical questions. So please try double check your answers. You will be able to, so as it's open book, you'll be able to, navigation will be, navigation also, what I will do, navigation among the questions, it will be enabled. Actually, all the questions will be presented to you in one page. Okay, so you'll be able to just scroll up and down. Questions will not be in different pages. I will arrange the midterm exam so that you'll see all of the questions on a single page as a quiz with 10, 15 questions. The number of questions is not finalized yet, so that's why I'm saying it's 10 to 15 questions in 2 hours. The homework 2, that's a very good question as well. So the homework 2 is going to be posted today. It's a very simple homework. It's going to be due 2 days after the midterm exam, probably 2nd of May, but use the homework as a study material for the midterm exam. It will contain topics that are in the midterm exam, and it will have very easy questions, 3 questions in the homework, just like it will be just like a longer quiz, the homework, but you'll be able to do it. We'll just spend 1 hour on the homework and you'll be able to do it. All right, so it will be announced today. That's the plan, but I don't know whether the assistant is going to be able to post it today, but today or tomorrow you should get your assignments these days, homework 2, and it's going to be again a written assignment similar to homework 1. and it will be due like 2 or 3 days after, depending on when we post it. It will be shortly due after the midterm exam, but I suggest you do it before the midterm exam so that you practice for the midterm exam. Oh, by the way, on Tuesday, I just noticed that you had the logic design midterm exam after my class ended. So that's why I was surprised at the end to see, the whole class had like 8 students. So it was surprising for me, but I would have wished you good luck. But I just noticed in my calendar after the class ended that you just have a midterm after our class on Tuesday. I could have left you early if I have noticed it earlier. Sorry about that. But I hope you had a nice logic design exam on Tuesday. And hopefully next Friday there will be no surprises. I mean, we are not trying some trick questions or anything in our midterm exam. So we hope everything will run smoothly next Friday at 4 p.m. All right, so yeah, any question? It will include topics all the way until the end of chapter 8. So chapter 8 is included in the midterm exam, but not chapter 9. So if we start talking about chapter 9 next Tuesday, they will not be included. Those topics will not be included in the midterm exam. And also, I may spend like 1 hour next week to solve some example problems in one of those classes. On Thursday. Well, Thursdays, 1 hour in Thursday, I can spend it to solve some exercises at the end of the chapters. I mean, of course, from the first chapters 2, 3, 4, and 8. Just some practice for the midterm. I can spend 1 hour for that. All right. Other than that, you are going to have the weekly quiz again available this evening at 6 p.m. You'll have again 1 day until tomorrow, even at 6 p.m. to work on the quiz. It will be a question about the central limit theorem and I think normal distribution, but it's going to be about chapter 4. All right. Any other questions? No, thank you for your attention to this class. And hopefully, as I said, you will learn something at the end of this semester, and you'll see why statistics and probability is important later years when you take other technical electives or you conduct some graduate studies. All right, thank you very much. And let's continue with today's lecture, which is chapter 8 in the book. It's the first part of the statistics, part 3, statistics and introduction to statistics. If you look at the, let me also change my mouse pointer size. All right, so if you take a look at this, the outline, it's composed of 3 sections. Population. At first, it describes what is a population, what is a sample. Usually, sample, as it's a singular term, there may be misunderstandings about what we mean about a sample. Sample sometimes is confused with a data point. A sample actually is a set. Okay, so a sample is a set of like outcomes. It's like an event. Okay, so sample is like you perform an experiment, you collect some data points from the population, which is your entire outcome set. And sample is actually, it refers to, the term sample refers to a set of data points. Okay, so this may be a little bit, as I said, misleading because as sample is a singular term, it may easily, I do it myself a lot. I mean, just to indicate a single data point, I sometimes use the term sample. But sample, when we talk about sample, a sample is a collection of a certain collection of data points from the population. For example, if we select 200 students from METU and to get some demographic information from them, for example, those 200 students, that's a sample. Okay, so 200 students is our sample. And each of those students in that sample is like our data point. And we are going to talk about terms like parameter. What's a parameter of a population? Statistics about samples. Okay, so and then we already know what mean is. It's like the average or the expected value here in probability. We are also going to learn new things like median, quantiles, percentiles, quartiles. So you may have heard like things like if you're a tall person, you may be saying that I'm in the top 1 percentile in the population, which means that basically you are taller than 99% of the population, or there are 1% of the population is taller than you. So we use these quantiles, percentiles, or there are some specific quartiles, the first quartile, second quartile, which indicates basically the 25 percentile, 50 percentile, 75 percentile. We are going to talk about these things. And the variance and standard deviation of the sample, the sample variance, sample standard deviation, we are going to see how we can have compute these things, which will be estimates of the population parameters. For example, when you collect a sample from the population and when you look at the sample variance, you're basically trying to estimate what the population population variance is. So each time we collect a sample, we are having an experiment and we are trying to estimate what the actual population parameter is. And these sample variance and sample standard deviations, they are random variables themselves, right? Imagine you try to compute the average age of METU students and you collect 200 students and you look at their average, that's your sample mean, and you use it as the indication, as an estimate for the average age of METU students. So METU students is your population. When you use the average of those 200 students, average age of those 200 students as the estimation of your METU population, age of the METU population, that becomes an estimate. And that estimate is going to change when you collect different 200 students, right? Each time you collect, do the experiment again, collect another sample with another 200 students, you will get a different average. Therefore, that average that you compute for that sample, that's a random variable. Imagine each time we collect that 200 experiment, we'll get something else. So it becomes a random variable itself. So we are going to talk about the standard errors of these estimates because that's a random variable. That basically standard error of estimate is the standard deviation of our estimate, standard deviation of our average. Each time we collect a 200 sample and we just write the average somewhere, someplace. We collect another 200 sample, we write the average at some place. If you look at those averages, the standard deviation of those averages of the samples that we have collected, that's called the standard error. So usually when we are doing estimation, we want the standard errors as small as possible, and there are things like unbiasedness of the estimate. So we are going to learn concepts like bias, consistency, and also the standard error of our estimates. The interquartile range is the range between the first and third quartile. It's, in other words, between the 25th percentile and the 75th percentile. We are going to talk about these things, and we are going to learn these histograms, stem and leaf plot, and box plot is used a lot to visualize data and shows the distribution of data points really nicely. You're going to take a look at those. And I think we're not going to talk about scatter plots or time plots, but you can just read them later yourself. All right, so let's go ahead and cover all these topics one by one. Okay, I actually summarized everything we're going to talk about. Uh, Very good question. So Berat Furkan asked, when we are taking these different samples and calculating their averages, is it kind of a normal distribution? That's a very good point. We can actually apply the central limit theorem because the average itself is collected. If you're always taking a sample with sample size of your sample size is 200 all the time, okay, the average itself, you sum the ages. Each student's age and the individual student's age is also a random variable, right? The age itself may be coming from different distribution, but when you collect the average, when you compute the average of those different ages, that's by applying the central limit theorem. You can see that the averages are going to be, I mean, the sums of 200 students, they will be normally distributed. And we will, with the central limit theorem, we'll be able to do that. So we can actually answer questions since they are normally distributed after we compute the standard deviation of our, if you know the standard error, if you of yours, actually you will be able to compute the standard error without actually uh, taking lots of 200 size 200 samples. Even for a single 200 sample case, you can compute the standard error if you know the standard deviation of individual students' ages, right? If that is given to you as some sigma, you remember the formula square root of n sigma that we use a lot in the central limit theorem? We can actually apply that. If we were given the individual student ages have the standard deviation of sigma, we will be actually compute the standard error by applying since the average itself is a summation of those individual standard deviations. The standard error will just be square root of n times that standard deviation of individual students' ages. If that's the standard error, then if that's the standard deviation of this average that I compute for sample sizes of 200, then I can answer questions like, what is the probability that um, the average that I compute, for example, the average that we compute, for example, based on standard error, we'll be able to say with what probability I am this much close to the true population average. So we'll be able to actually use that's a normal distribution, and we'll be able to assign some confidence to our estimations. When it's 200, when the size is 200, for example, we will be less confident. When the size is, for example, 1000, we'll be more confident because every time we are going to see that when we compute this is called consistency about the estimator. Uh, we'll see that in the average, especially, we are going to be more confident. We are going to talk about these things in chapter 9. Okay, but that's a very good point. When the estimator that we may estimate something by using some summations and averages, central limit theorem will be applicable, and we will make use of the normal distribution. So that's why normal distribution is very important. So yeah, let's go ahead and continue with these standard definitions. As I said, chapter 8 is fairly easy. It's just a bunch of definitions, but it's important. It's easy. It's an easy chapter, but it's still very important to understand these terms. When we say population, in order to talk the same language, in order to understand the question unambiguously, you need to know these terms. So these terms are like our contracts, are common grounds. When I say sample, you should really understand it's a set of data points, not a single individual data point. When I say population parameter, it's like variance, mean, you should understand about that. And when I say statistic, it's some numerical value computed about a sample. So these things are actually on the slide, but let's go ahead and go over them one by one in a systematic manner. So the area of statistics focuses on data collection. It's about data. So data science, actually, if I'm not mistaken, the Department of Statistics in our university, they changed their name, the undergraduate program, the Statistics and Data Science. All right, so that's really statistics is a data science. So actually, they didn't need to change their names because statistics itself is about data science. But since data science is a really hot term these days, buzzword, so to maybe attract better students, such a change to make it explicitly indicating that it's data science may be something reasonable thing to do. So it's about collecting data, analyzing data. There are visualization techniques, estimation of the distribution parameters of the population, finding correlations between different data, finding correlations between parameters. For example, whether so this correlation. I mean, there's also lots of application of this to finance. You may guess. For example, future predictions for certain stock market changes. And also by using this standard errors and computing that some of our parameters are normally distributed, we'll be able to assess the reliability of our estimates. We will be able to assign confidence levels to them. And we will be also testing statements. So these last two bullets, they're all chapter 9. We'll have some statements about the parameters. We'll say that, for example, if somebody makes this claim, electrical engineering students have higher GPA than computer engineering students. That's a claim, right? So we're talking about two parameters, the GPA of a population, two different populations, electrical engineering students, computer engineering students. These are, when we talk about this, these are two populations. So when you make such a claim, you usually, I mean, what you can do is, if sometimes when you can collect data almost about the entire population, but when you make such a claim, you don't actually know what the coming electrical engineering students will be in the coming years. And if you make this statement saying that the electrical engineering students in the last 10 years have higher GPAs than computer engineering students, you can actually still get the entire population data and take a look at whether this is true by just looking at the average of those cumulative GPAs. But usually what we do is, when we have such a statement, we collect a sample, like look at the GPAs of 20 students, 30 students, and our hypothesis will be that, for example, the mean of those EE students, mean of the GPAs are higher than, the mean is higher than the GPA of, for example, computer engineering students. But that claim, that's called a hypothesis, and we test this hypothesis by actually trying to reject some null hypothesis. Then our null hypothesis in this case will be they are equal. All the null hypotheses are always about equality. We'll first indicate that the null hypothesis is like the opposite of what we try to test. We'll say that, okay, let's have this null hypothesis that their GPAs are equal to each other. Okay? If we cannot confidently reject the null hypothesis, it means that we cannot claim that electrical engineering students have higher GPA. So we'll talk about these things. That's, as I said, the topic of chapter 9. We'll see hypothesis testing like this, and we'll be able to see how confident we can reject the null hypothesis is going to tell us something. It's always, we'll not make any certain statements about these things. We'll say that, for example, at this confidence level, I cannot reject the null hypothesis. But if you decrease your confidence level, maybe you can reject the null hypothesis. So it's going to be about some confidence levels, but we'll make statements about probabilities, because what we do is we collect sample data, and that those sample may have errors in them. That's why we will never be probability and statistics. You never talk certainly about certain things. You always leave room for some error. So yeah, here's some terminology and notation. Yeah, let me see what time it is right now. So we still have 20 minutes until the break. So let's go ahead and continue with the slides. So population is this, as I said, it's a set of all possible sources of a random variable. It's like your entire sample space. Not the sample space. The sample space is actually, if you remember, random variable is some numerical value about an outcome. So we first map each outcome to a random variable. For example, the our outcomes may be the students themselves, but the random variable in that case is the age of that student. Age of a student may be a random variable, and if you just collect one data point, one outcome, a single student, and ask their age, you turn it into a random variable, a numerical value. So the set of all possible, so the entire population is basically our entire set of random variables that the values the random variable can take. We usually, most of the time, when we make claims about population, we don't have direct access to the population data. That entire set of outcomes in the area of statistics, that's something not attainable to obtain the entire data about the entire population. So for example, we talked about the efficacy of these COVID vaccines these days, right? Can you try the efficacy of those, efficiency, accuracy of those vaccines for the entire population? You have to conduct tests for the entire population, and there are people still being vaccinated. So the population, you don't have the entire population. So what you do is you conduct studies on people, like 10,000, you collect a sample of size 10,000 and you compute the efficiency of the vaccine on those 10,000 people, and then make some claims about the population. Okay, that's the population, and the entire population is usually collecting data on the entire population. Most of the time is time consuming, costly, and therefore in statistics we collect data and we make claims about the population on that data. But one important thing is if you have an estimator which is consistent, we are going to talk about this term. It means that as the sample size gets larger, you're getting closer and closer to the actual value. There are certain, I don't know whether we have such an example in the book, but if your formula, if your averages are consistent, but you may think about some other mathematical parameters, some statistics about a sample, which may behave differently. They may not converge to some number as sample size gets larger. In such a case, the parameter statistics that we compute may not be consistent as the sample size gets larger. If it's not converging to the actual value, we'll call that as an inconsistent estimator. But most of the examples we are going to see in this book, they're going to be both consistent and they're going to be unbiased. So when the term parameter is any numerical characteristic of a population. For example, mean, variance, population mean, population variance, those are population parameters. Standard deviation, so those are the most basic. So, but any numerical value about a population, the random variable, you may consider, we call that parameter. And sample is a subset of those random variables from the population. So a set of observed sources from the population is called a sample. And a statistic is that computed population parameter. So it's like any function of a sample. You get your sample, you compute something similar to a parameter. So a numerical characteristic, you compute that for that sample, that becomes a statistic. Where, for example, a sample mean is a statistic. Sample variance is a statistic. Or the fact that the median of that sample is this number is a statistic about the population, about that sample. So statistic is computed, something we compute out of a sample. And usually the way we indicate these things is this theta you're going to see a lot. It's used as a generic term or generic variable to indicate any parameter. So this theta will sometimes be mu, mean. Sometimes it's going to be sigma, the standard deviation. So sigma, mu are some specific. So let me write it through here. So theta is just the most in general term. That's the most general occurrence of some term. It may be mu, sigma, or variance. Okay, so that's what theta is about, something about population. And we are going to use the term theta hat to indicate the sample statistic, the estimate for theta. If we have an estimate for theta, we indicate it with theta hat, and we may compute this theta hat may be coming from some sample statistic. So we may compute this time, for example, x bar. Okay, x bar is going to be the same. Is going to be an estimate for mu, and we are going to have s, the small letter s. It will be the sample standard deviation, which is going to be an estimate for the sigma. So mu, sigma, sigma squared, they are things that are known certainly. Sometimes for a population, if mu and sigma is given to you, you know those parameters about the population. But in real life, in practice, we don't know these mu and sigma. But we use sample statistics, x bar and s, as an estimate for mu and sigma. So that's how they're related. So as I said, this is a generic term. Theta is a generic term for any population parameter. Theta hat is an estimator of data calculated using a sample. So there are really simple ways to simpler estimators for theta hat, but there's something that is interesting. The sample standard deviation is, unlike average, is not divided by, it's not the average of the sample. So we are going to see how it's computed. We are going to be, in order to have an unbiased sample standard deviation, we are going to be dividing by n minus 1, not n, as we do in average. We'll see about that, and let's see how the book proves this thing. But this figure also shows the relationship between a population and a sample. So from a population collecting data, we get a sample. If we have a sample, we can directly compute some statistics about the sample, like x bar, the standard deviation of sample standard deviation, sample variance. These parameters most of the time are not directly known to us. Mu, sigma, sigma square are the parameters of the population. And when we do inference about the population, this is what we do, is called estimation. And sometimes we compare two things, we test something about the population, saying that the population mean is equal to 50. That's a claim. Okay, so when I say that the population mean is equal to 50, that's or greater than 50, that becomes a hypothesis about the population, and we are going to see with hypothesis testing we'll be able to test these hypotheses, and we can do modeling, future predictions about population and such. When we are doing sampling, so these arrows here, when you're collecting data from population, that's also called sampling. From the population. When we're sampling from the population, we need to be very careful when selecting the samples. There may be biases. For example, when you're conducting some surveys, questionnaires about who's going to vote for which political party in the next election, when you're collecting data, when you're asking the individuals that you see on the street, there may be biases. Okay, so you really need to cover, in order to cover the entire population, you need to visit different parts of the town, different big cities, small cities, different age groups. So there are the demographics of the sample that you choose. Really, in order to be unbiased, you should try to get samples from everywhere. Okay, so in order to reduce this bias. And also for example, when you select a sample, an individual from a family, if you select your second data point from the same family, those two samples points are not independent from each other. they have influence on each other. So in order to be independent, you want the data points that are in a sample to be independent from each other as much as possible. So the dependencies between data points should be reduced as much as possible during sampling. If you do that, your sample will be a good representative of the population. Otherwise, obviously, so this is really something intuitive. Actually, it will be biased, and it will not be a good estimator of your population parameter. So in general, any sample is an approximation to the whole population, but if you do it correctly, larger the sample size, the number of, this is actually the number of samples. As you see, I use the term incorrectly. The number of samples, I use the number of data points. So I use the term that I told you that you have to use the term sample correctly, but here I use the term samples as if they're data points, right? So I should say here, I should correct the statement that as the size of the sample increases, the approximation error should decrease in general. So simple random sampling most of the time works. For example, if you don't know anything about who lives who, if you get the entire Turkish population and their, for example, national ID numbers and select, if you have those national ID numbers in an array and sort them, and if you filter them, for example, first to have everyone over the age of 18, anyone who can vote, if you have the national ID numbers of anyone who can vote, and if you shuffle that array and uniformly sample from that array, and that's because if that becomes your sample, I think that's going to be a good unbiased sample. Using that sample, you'll be able to estimate the population parameters in an unbiased manner. Here, this term, independent identically distributed sample, or IID, is the term we use when we have these unbiased random samples we collect from the population. When all data points are equally likely to be sampled, in other words, it's like a uniform distribution. Actually, since this is a discrete distribution, right? For example, if you have 100 individuals, if the population itself, and it's really large, again, it's going to be still a discrete distribution with every individual having the chance 1/80 million, for example, to be sampled. If they're all equally likely, this will be more like a binomial distribution, or each of them will be like a Bernoulli trial, whether they are going to be included in the sample or not. But yeah, anyway, the main point here on this slide is to have them as random as possible, equally likely selected to reduce biases. So, and the descriptive statistics that we are going to talk about a sample, mean of a sample is really simple. Median, what we mean by median, quantiles, quartiles, variance, standard deviation, and this interquartile range. It has the unit of whatever population parameter you are measuring. Each statistic, as I told you, that it's a random variable, because different samples, if you get a different sample, compute the same statistic on that sample, it will result in different value because it's a random experiment. Therefore, a statistic about computed using a sample is a random variable itself, and its standard deviation is called standard error. And if you look at the distribution, our estimate is, for example, the averages, you'll see that they are normally distributed. The sampling distribution in that case will be normal, but depending on what type of statistic you are computing, if they're not about sums, for example, imagine we collect a sample and we just compute the maximum age of a student in that sample. Is maximum. It's not sum. We just use the operator maximum. Okay, that's a function. That's a mathematical function. Maybe our uh, goal may be what is the maximum age in this population. In order to do that, we use this max term on a sample that we collect, and we hope that that's going to I mean, as you can see, this is not a very good estimate, right? If you collect 200, if you really want to get them have the maximum age in a population, you actually look at on your entire population to find that max. But imagine we try to do that by using sampling. Get 200 students, find the maximum age in that student. So if you look at those max values every time you take a sample, is it going to be normally distributed? Not necessarily, right? I mean, because central limit theorem does not apply here. There's not about sums, averages. It's just the maximum of some set of values. But if you look at how those maxes from different samples are distributed, in general, it's called the sampling distribution. It may have a different type of, it may be different from the family of distributions that we have seen up to now. So in general, the general term for such statistics distribution is called sampling distribution. But for many of these things, like for standard deviations, the population averages, they will be, most of the time, they will be normally distributed. So the sampling distribution will be normal for mean. So mean is really simple. It's just the average of the individual data points that whatever you just look at the random variable for your individual data points, and their averages is the population, is the sample mean. This mean actually we have to be specific, and this slide should say sample mean, okay? Because mean, the term mean is also used for the population too. So therefore also standard deviation too. Usually these terms should be preceded with whether you're referring to population or the sample to indicate sample mean or population mean or population standard deviation or sample standard deviation. So sample mean is unbiased. So look at these terms. Being unbiased, what does it mean? Being consistent and asymptotically normal. So asymptotically normal is coming from the central limit theorem. As n gets larger, this is also what central limit theorem tells us, that as n gets larger, its distribution of x bar is going to be normal. If you look at it for a specific set n, if you set n to some number, for example, and look at the distribution of this x bar, you're going to see that it's going to be normally distributed. I'm going to describe these terms. Being unbiased means if the expectation of an estimator is equal to the estimated parameter. So there's something interesting, right? What is the expected value of our estimator? So that's really interesting. So we haven't told, since it's a random variable, we can talk about the expected value, right? Random variable, since this theta hat itself is a random variable. Now we can talk about what is the expected value of that random variable. And this is something, so this specific thing, the x bar that you compute here, is not the expected value actually. It's like taking, when you compute a single theta hat, it becomes a single observation in your theta hats population. There are different theta hats. Since theta hat is a random variable, each time you get a sample, you get a different theta hat. Now, since that's a random variable, we can ask what is the expected value of that theta hat. So if it's equal to theta, it means it's an unbiased estimator. But how can we compute this? For example, we can compute, in order to compute the expected value of theta, you don't need to actually collect the sample if you're given how you compute this theta hat. For example, for x bar, we can compute the expected value of x bar, right? By using linearity of expectation. For example, if the population, what I mean is that, look at this x bar and xn. They are also like individual data points here. So this x, individual x's are random variables themselves. If you know, if you're given the expected value of x1, what is expected value of x? Any x. So let me actually write it here instead of, so the expected value of x, it's our mu, right, in a population. So if we're given this, the expected value of this is mu, all right, each one of them, and we don't know what mu is, all right, but this is something given. If we know that the expected value of an individual is this, that's the population parameter, mu. If you try to compute this, what is the expected value of x bar, you will be given this. Given this, is it? Can you compute the expected value of x bar? Yes, by using linearity of expectation. What is the expected value of x bar? It is, you just write them individually. So since these x1, x2, x3, xn are coming from the population, each of them are actually have an expected value of mu. So it's this, okay, which is equal to, because of linearity of expectation, expected value of x1 plus expected value of x2 all the way expected value of xn divided by n. This is what I have here from linearity of expectation. Since each of these are mu, I don't know what the actual value of mu is. I'm just mathematically doing something. I'm just replacing the variable here, which is going to be n times mu divided by n, which is equal to mu. So what is the expected value of x bar? It's mu. So what does this tell me? X bar is an unbiased estimator for population mean. All right, so this is how you can actually, without collecting actual data, you can prove by just looking at its mathematical function, the function of this mean. By looking at it, you can say that, oh, it's an unbiased estimator because the expected value of my x bars are going to be mu. So it's an unbiased estimator. And in general, bias is the expected value, bias of an estimator is the expected value of the difference between theta hat and theta. And if this, again, because of linearity of expectation, you can write this as expected value of theta hat minus expected value of mu, since this is a constant number. Theta here is a constant number. It's not a random variable, okay? That's also an important terminological distinction between theta hat and theta. Theta or mu specifically, so theta was a general term. If you think about mu, mu is not a random variable, okay? Mu itself is some population parameter that is fixed. That's not a random variable. Mu doesn't change. We may not know what mu is, but mu is not a random variable. So therefore, the expected value of mu is equal to mu. If the expected value of theta hat is also equal to mu, this minus this is going to be 0. So unbiasedness means that the expected value of this thing is equal to 0. And consistency, actually, we've already now come to break time. Let's have a 10-minute break until 10:45. I will stop recording and I will talk about consistency. And there's a nice figure I have here. Where was it? That's, yeah, here. When we were talking about standard error, actually this figure also shows how what we mean by unbiasedness, but it also shows, first we need to talk about standard deviation or standard errors of those estimates, then this figure will make more sense. This is from the book, by the way, but yeah, let's go step by step. And we were right here. We've just shown that x bar sample mean is unbiased. Then we're going to talk about consistency after the break at 10:45. All right, so I will stop recording now.